So this will be a lecture in Z-transforms, all part of Chapter 5. It's our fourth lecture. We will talk about solving linear difference equations, do several examples, and then we'll make some comments on the transfer function for discrete time systems, a little bit on stability, and wrap it up with another example in which we find the unit impulse response for a discrete time system. So let's look briefly at a process of how we would go about finding the solution to a linear difference equation. So this is all about solving linear difference equations. Using the Z-transform, using Z-transform methods. We know that solving difference equations is a bit tricky in the time domain. We can use recursion, which is easy, but recursion doesn't yield a closed form solution. We can use the closed form solutions, but they're awkward in the time domain. Transform domain gives us a much simpler way of solving these guys. What I would like to do is just summarize the basic steps, and then we'll show how it's done through an example. So if it's not already in there, you do want to put your system description in delay form. So go ahead and draw it out in delay form or write it in delay form. Delay form is going to be the easier way to work with these equations. We know that we're going to be applying some sort of causal input, so apply causal input. If it wasn't causal, you could shift it so that it was, and then just change your frame of time reference. So apply a causal input. We want to be able to handle these difference equations with initial conditions is the example we're going to be working with here. And because we want to deal with initial conditions, we want to use the unilateral Z-transform. And that does require this idea of causal input, or something that starts after 0. And then once we've got that causal input in there, we want to solve, right? We want to solve this guy for all time n greater than or equal to 0. That's like multiplying by a u of n. That's what's going to be the thing that's going to allow us to use that unilateral transform. So all of this is going to be utilize the unilateral Z-transform. So our goal here, right, is to solve a linear difference equation for some input with some initial conditions, and to do so through the Z-transform methods. So let's do an example of this. It's an example that is very similar to stuff we saw for Laplace, just a discrete version, and the techniques themselves actually have a lot of similarity to what we saw in Laplace as well. So I'm going to start out with a kind of a standard form difference equation in this particular case, where that standard form difference equation is written in advanced form, which is kind of the preference of this book. So I'm going to have a y of n plus 1 minus 1/2 y of n being equal to, let's just make it x of n, something simple. And let's go ahead and let, in this particular example, the input x of n just be equal to the unit step. So we essentially turn on a light switch or apply a battery, and we're going to let there be some initial energy in this system reflected by an initial condition, y minus 1 being equal to, oh, let's just give it a value 2, something like that. So I would like to solve here. I would like to solve this system, right? And to do that, what I would like to be able to do is I'd like to be able to find the y0 input response as a function of n. I'd like to find b, the y0 state response of n, and c, let's go ahead and find the y total as a function of n as well. So I'd like to find out what does the system output just do to the initial conditions. That's the 0 input response. I'd like to find out the output that is just due to the input, so that's the 0 state response. And then I'd like to find out the total response. That's the output that's a result of both the input and the initial conditions. Turns out we can solve for all three of these in a single step, as long as we pay a little bit of attention to what sources of energy go where. So let's go back to our steps here. It says put our equation in delay form, and then we're going to apply that causal input and solve it for n greater than 0, kind of like multiplying by a u of n, and just applying the unilateral transform. So in our particular case, we had a difference equation, right, that was in advanced form. So our difference equation here was in advanced form. I would like to go ahead and delay that thing and get it into delay form. So If I do that, I'm going to get y of n. I just delay everything by 1. And I'm going to have a minus 1/2 y of n minus 1 being equal to x of n minus 1. I've got a delay form difference equation now. I'm going to go ahead and apply the unilateral z transform to this guy, and that's going to give me y of z for the first term. I'm going to have a minus 1/2. When I take that y of n minus 1 and I z transform it, I can go ahead and pretty easily take a look at what that thing transforms to. And I'm going to get a z to the minus 1 that just says delay by 1, y of z. So delay by 1, that y term. And then we also get, in this particular case, a dependence on the initial condition. So we have a plus little y of minus 1. So you can get that right off of the property form. And then that thing's going to be equal to, on the other side, we are going to have z to the minus 1 because we're delaying x by 1, right? X of z. And you could come in here as well and have something like that, little x of minus 1. But we know x was a causal input, so there should be no previous values of x before n equaling 0 that are non-zero. So that's just going to go to 0, something along those lines. Okay, so we've gotten to the z domain, and one of the things that we notice here is by applying the z transform, as hoped, that delay, which made it really hard in the time domain to solve for y of n, because you got y of n term and then you've got a y of n minus 1 term, and you just can't easily solve, at least not algebraically, for y of n. You can't get that delay away from the variable of interest. When we go over to the z domain, that delay gets stripped away from the variable of interest, the y, gets stripped away in a way that can be algebraically handled. So the delay becomes a multiply by z to the minus 1, and we'll be able to algebraically deal with that. So I'm trying to find stuff about my output y. So I'm going to collect all the things that have that output y. So I'm going to have y of z, and the first part that had that, there was just a 1. That's the first term out there. And there's a minus 1/2 z to the minus 1. And so we've got all of that. Our y of minus 1, we had seen that before as well when we had first laid out the problem statement. Our initial condition was 2. I'm going to go ahead and make a substitution of that in right now. So I had in here my y of minus 1, that's going to be 2, and that's going to get weighted by a minus 1/2. So 2 times minus 1/2 is going to be a plus 2. And I will end up getting then that, not a plus 2, I have a 2 times minus 1/2, that'll be a minus 1. So I can put my minus 1 in there. And then on the right-hand side, I'm going to have z to the minus 1. And then I do need that x of z. And if I take a look at my x of n, it was u of n. We could certainly look up in our table of z transforms or do it by definition if we wanted. We've done that example before in a previous lecture. So the transform of u of n, we know to just be z by z minus 1. And so I'm just going to do a couple of things here. You don't have to. I just would like to make sure that we are keeping track of a few of these things. So I'm just going to notice something here, right? That this minus 1 term came out of the initial condition, right? And this term over on the right-hand side was because of the input, something along those lines. And I'm going to leave these terms separate because it's going to allow me to separate out the output component for each of these two sources of energy in the system. The energy internal, that's the initial condition, or the energy externally applied, that's the input. So if I continue, I'm going to bring that initial condition term over to the right-hand side, and I'm going to get a y of z, and I'm going to have 1 minus 1/2 z to the minus 1 being equal to, then we have our z. Well, let's go ahead and take care of that as well. If I take z to the minus 1 times z, that's just going to give me 1, and I'm left with a 1 by z minus 1, and then I'm going to have a plus 1. Again, if I wanted to just maintain a little bit of accounting of where things came from, that 1 over z minus 1 came from the input part, and that 1 came from the initial condition, something along those lines. Now I'm going to go ahead and divide both sides by that 1 minus 1/2 z to the minus 1. That will leave just y of z on the left-hand side. So I have y of z on the left-hand side, and that's going to be equal to a 1 by, and I have my z minus 1 in there, and then I'm going to have a 1 minus 1/2 z to the minus 1, and then I have a plus, and I'm going to have a 1 over 1 minus 1/2 z to the minus 1. Just a reminder, and if you take a look at this guy as well, If you look at this piece right here, that was the thing weighting y of z, that is totally related to my characteristic polynomial from my difference equation. So that does have some relation to q in there. And so we know that that's going to control a lot of the mode-like terms that come out in the output as well. So just a quick reminder that the characteristic equation again comes into play. All right, well, I'd like to clean this up just a little bit. Both of these have kind of got a mixed rational function, so there's some positive powers of z, some negative powers of z. I'd like to go ahead and get them all in terms of positive power of z. That will match our tables anyway in here. So I'm going to go ahead and multiply both of these guys by a z over z. That's just a big fancy one. So I can take this whole right-hand side, multiply it by 1. Multiplying by 1 doesn't change anything. And if I go ahead and distribute that out, I'm going to get a z over, and I have a z minus 1. Take that denominator z, multiply it through this the second portion here, and I'm going to get z minus a half. So that's just going to return everything to positive powers of z, so z minus a half. And then same sort of an idea on the last term over here. I'm going to get a z in the numerator, and I'm going to get a z minus 1/2. Again, I'm going to do my accounting here and just remind myself that everything that is on this first term came as a result of the input being applying. There were no initial condition dependence on that. And everything over on the second-hand term had to do with initial conditions. There was no input related terms included in that. And if you remember what we've got on the left-hand side, it's just the variable of interest, the output, something like that. What did we know when we looked at discrete time systems back in chapter 3? We knew that y total, right, as a function of n, could be thought of or broken up into two parts. It could have its zero state response, so the things related to input, and it could have the zero input response, those things related to the initial conditions. And guess what? That's exactly what we have here. We have the transform domain of my output, total thing. It involved both input and initial condition. And we see that it's broken up into a piece that has only got something to do with the input, no initial condition. So that is going to be my zero state response. And then I also see that I've got a component that has only to do with the initial conditions, right? Nothing to do with the input. So that's my zero input response. So just by maintaining my terms, I'm keeping the pieces separate, those pieces that came from input parts and those parts that came from initial conditions parts, I'm able to find both the zero state and the zero input responses using the Z-transform method. Okay, so now I'm ready to invert. So what do I know? I know that I guess I'm not a capital Y now, I'm going to be in a lowercase. So I'm going back to the time domain. So I'm coming in here and I'm going to be doing an inverse Z is what I'm hoping to do. Well, I'm probably not quite ready for that either. So let's go back and fix this just one more time. When I take a look at this, this second, this zero state response term, I'll circle that right now just so we know what we're talking about. That's not directly in our tables. It's got two real modes, two real roots down in the denominator. We probably want to break that guy up. So let's go ahead and do a partial fraction expansion on this guy as well. If I wanted to, knowing the kind of problems that I have with partial fraction expansions, doing it in the standard way, I could do this as a modified partial fraction expansion. So I'm going to take a y of z by z, and I'll just go ahead and do that very quickly, y of z by z. Well, fortunately, when I divide by z here, you'll notice that the numerators in both of these cases had a z, so dividing by z is just going to make those guys disappear, and I'm going to be left with a 1 by, and we look at the roots in there, I have a z minus 1, right? And I have a z minus a half. And I didn't really have to do it with this other term, but I'll go ahead and keep it just so the math works out. I have a 1 over z minus a half. I'm going to go ahead and now do a partial fraction expansion, that modified partial fraction expansion on this first part. So I'm going to have something over a z minus 1 plus something over a z minus a half, right? And these guys are all, as we recall, this is all part of the stuff that had to do with the input term. So this is going to be my zero state response. And I need to just find the coefficients for these two pieces. I can use like the cover up method. If I cover up, for example, the z minus 1 term and then evaluate that overall fraction, it's a strictly proper fraction, so I can do this. Evaluate that at the root z equaling 1. I'm going to get a 1 over a half. That's going to be a value of 2, so I should be able to get a value of 2 up in here. If I go through and I cover up the other one, that's going to cover up the z minus a half. I evaluated the root. I'm going to have 1 over a half minus 1, so that's going to be 1 over minus a half, or a minus 2. So I would have a minus 2 in there. If I cross multiply in there, I would get 2z minus 2z, so no z's up in the numerator. I'd get 2 times minus a half, that would be minus 1, and I'd get minus 1 times minus 2, that's 2. 2 minus 1 is 1, which is the original numerator, so this thing checks out. The last term then, right, didn't need to do much with that. That's a 1 over z minus a half. And this whole thing, remember, this was the modified partial fraction. That's y of z by z. Now I can multiply everything by just z, return it back to an expression that is y of z, and I'm going to get 2 times z by z minus 1, and I'm going to have in there I guess that's a minus sign, so we'll go ahead and make that minus, a minus 2, and I'm going to have z by z minus a half, and then I have my z over z minus a half. Now I'm ready to invert transform these guys. And just a reminder again of where we were with the other term over here. This one was due to the initial conditions. We're keeping those guys separated, right? So I still have that initial condition term. I still have the input term. If I didn't want to be keeping them separate, notice that there are a couple of terms that could get combined. They could get combined. They both have the same root. Both of these are going to give me a 1/2 n u of n type term. I could combine those together, but once I've combined them, I'm never going to be able to separate them back out to find out which part was because of the input, which part was because of the initial condition. I want to leave those separate just because of what was asked for originally. So I get out of this what? The inverse transform, the inverse unilateral transform, gives me my time domain signal, in this case y, then that's the total response. That first term there, z by z minus 1 is a u of n, it's weighted by 2, so I'm going to get a 2 u of n, right? I have a minus 2, the root there is a half, so I'm going to get a 1/2 to the n u of n. Again, you can get that straight from tables. And then that last piece in there is going to be plus, and I'm going to have a 1 times a half to the n u of n. I'm now going to go ahead and bracket certain pieces. That 2un minus 2 1/2 to the n u of n, that is my y, what? Zero state response of n. It's the stuff only due to the input. So that's my input driven output. And then if I look at my other piece, the 1/2 to the n, that's comprised only of the natural mode of the system. We know that when you stuff energy into a system, it can only respond according to its natural modes. It's built into its DNA, it's built into its character. That is the Y0 input response as a function of that. Everything due to the initial conditions, nothing to do with the input. So this is my initial condition driven output. This one on the left is my input driven output. Something like that. And we've got everything broken together. Now, if I wanted to just have a simplified expression for my y total, right? Y total, I could do that if I wanted, but the second I combine everything together, remember it's going to be really tough to undo it. So my total response to u of n in simplified form is going to be 2u of n, and then I have that minus 2 plus a 1 of the 1/2 n's. That's just going to be a minus, and I have my 1/2 to the n u of n. There's a term in here that looks a bit like the input driving function, right? So that's like this. That's the forced like response. And then there's stuff that looks like the modes of the system that comes both from the initial condition and because of the input being applied. That's our natural response. If you remember back to calculus, another way of splitting up solutions to things like difference equations or differential equations is maybe not zero input or zero state or homogeneous and non-homogeneous. There's such a thing as forced and natural. This is the forced and natural components as well. So if I finally box things up, I could go ahead and box this whole piece down here. That total response, if you go way back to the top of what we were asking on this thing, right? We had asked for zero input, zero state, and y total. So that y total down here was the thing out of C. The zero state response, I think, was the other one that we were looking at least as the second part, I think it was. So that's my B. And so if I look at my zero state response, something like this guy, that is my part B in this case. And then the last one, just that zero input response was my part A. And I'm done. And I did it all in one piece. Compare the workload here. Even though I spent a little bit of time getting through it, none of the steps was particularly difficult. Compare that workload to what we would have had to have done had we made this solution in the time domain. Just to get the zero input response in this particular case, right? If we think about that zero input response, this one sitting over here, you would end up having to find those natural modes, solve for the coefficients of those natural modes. To come over here and get the zero state response, you would have had to find the unit impulse response. That's not terribly fun. Then you would have had to take that unit impulse response, convolve it with the input, go through all that convolution process. Could have definitely gotten it through time domain solution methods, but it would have been a whole heck of a lot more difficult than what we just went through in this particular case. Okay, so that's an example of using a unilateral Z-transform, and built into that is some of the properties we talked about during our last lecture. But using the unilateral Z-transform to solve for our linear difference equations, a pretty straightforward process. Just write your equation in delay form, go ahead and apply that unilateral transform to it. If you want to keep the zero input and zero state components separate, just keep the corresponding terms separate from one another. If you're not interested in maintaining separation, you could have combined them together at whatever point was convenient to keep your workload low. Let's make a few other statements that we would want to point out. The system function is something that we talked about with Laplace. So the system function or transfer function is again a concept that we can employ whether the system is continuous time or discrete time. So let's look at and make sure that we understand this idea of a system function or a transfer function. The system function or a transfer function is something that really comes out of this idea of having a zero state look at a system. So this really corresponds to looking at a system that is at rest, right? And by at rest, we mean that the initial conditions are equal to zero. There is no energy stored into this guy. We know that we can represent this system in a delay or advanced form. I'm going to go ahead and show it in delay form. So we would have something like a1 plus an a1 e to the minus 1. That just says delay by 1 plus, and we go all the way out until we get to the order of the system, a sub n, and I would have e to the minus n. That whole thing is going to act on my time domain output y of n. Set on the right-hand side some b0 plus b1 e to the minus 1 going all the way out till I get to a bn e to the minus n. Running out of room here. That whole thing is going to multiply by my x of n. Ran a little bit short on space here. So I've just shown the difference equation, right, written in delay form. We could have definitely gotten this by doing something like the following. I could have taken e to the minus n times q of e, right, acting on y of n being equal to e to the minus n p of e acting on x of n. So using some notation we'd seen before, q of e is just the characteristic polynomial. P of e is like a characteristic polynomial, it's just the one that's operating on the input terms. And if I wanted to get it in delay form, I just delay the entire equation by n, which is really what this e to the minus n term being multiplied on both sides or operated on both sides gives us. Okay. So I have this delay form equation. I would like to go ahead and take either one of those, doesn't really matter, take either one of those guys, and I'd like to Z-transform. We're assuming this thing's at rest, so we don't have to worry about unilateral. I'm just going to take the regular old bilateral Z-transform in this case. And what I find is what? If I have just a signal, right, y of n, weighted by something, in this case 1, and I transform that guy, what do I get? I get y of z. So I know in that particular case, that first term, I'm going to do this a little bit backwards, right, gives me just y of z. If I have a1 y of n minus 1, which is what the next term is, so a1 e to the minus 1 acting on yn is just a1 y to the n minus 1. It's a delay by 1 y term. Well, that one's going to give me z to the minus 1, right? Because a delay by 1 just manifests as a multiplied z to the minus 1. Because there's no initial conditions, I don't have to have all those initial condition terms. Keep doing that term by term, and I can go along, and I find out that I go all the way out to a to the n, z to the minus n, and we end up getting direct substitution of those delay operators, e to the minus 1 through e to the minus n, being replaced by these frequency variables, z to the minus 1, z to the minus n, no problem in there. Do the same thing on the right-hand side, and I'm going to get a b0 plus b1, z to the minus 1, plus going all the way down until I hit a bn, z to the minus n, x of z, something along those lines. Let's go ahead and solve then, in this particular case, for the y of z. If I do that, I get y of z being equal to, I have the thing up top, that's b0 plus b1 z to the minus 1 plus all the way out until I hit bn z to the minus n, and I will have an x of z out as well, but I divided by that term out front. That was the 1 plus a1 z to the minus 1 plus going all the way out to an an z to the minus n, something along those lines. Just because of the way our book notation is, while we oftentimes work with equations, difference equations in delay form, our book prefers things in terms of positive powers of z. So again, I can play that same game. I can multiply top and bottom by z to the n. That's just a fancy one in here, and I can get something like this. I can get y of z equals, and I'm going to have what? b0 z to the n plus b1 z to the n minus 1 plus going all the way out till I hit just the constant bn. We're going to divide this by z to the n plus a1 z to the n minus 1 plus going all the way out until I hit an an, and this is going to be multiplying my x of z. You'll notice the numerator here, the b0 z to the n all the way down to bn, that's just my p polynomial, right? Where I've replaced the operator e with z, and the denominator we recognize as that q polynomial. So what do I get? I get y of z equals p of z by q of z, x of z. And what were we doing? This was all, right? This was all solving with zero initial conditions. So another way of looking at this, if you wanted to be just a little bit more complete, is that this is the zero state response. Transform domain solution, right, is some pz over qz times x of z. Let's call that ratio pz over qz. Let's just call that h of z, which I'm going to define as the system function, and we'll clean this up just a tiny bit. That's not a terribly great C. Let's make that a better one. The system function. Or if we wanted to, I don't know why that just happened, but let's get back down here. So it's a system function, or we can also call that, or we can call it the transfer function. That's just the terminology we use here, the transfer function. Okay. And so what we get here is the y zero state response of n is equal to h of z, the system transfer function, times the input x of z. If I invert transform this guy, right, invert z transform, what do I get? I get y zero state response of n is equal to the inverse transform of h of z. Let's just call that some signal h of n. Convolution is what replaces or comes out of multiplication in the transform domain. So convolution in the time domain becomes multiplication in the z domain, or you could say multiplication in the z domain becomes convolution in the time domain, and x of n. And we've already seen this expression before. We derived that back in chapter 3, So what do we see? We know the zero state response is the convolution of the input with the unit impulse response, and that if I just transfer that whole expression, I get a expression that is the z transform of the zero state response, and that is the system function h of z times the inputs transfer transform x of z. Looks like I do have a little mistake here. I want to clean that up. This is one that I definitely would not want to see persist. We were in transform domain there. There should never be an n over there. That was y0 state of z, right? So let's make sure we get that right. Something like that. So this transfer function h of z, right, is just the z transform of the unit impulse response. It is that factor that we can multiply an input by in order to get the zero state response. So going up and cleaning everything up, h of z, we know, is this transfer function equals the transfer function. Just to remind us, transfer function. And by the way, we saw this with Laplace as well, right? H of s was what we called the transfer function, and it was just the Laplace transform of the unit impulse response. Here we get the z transform of the discrete time unit impulse response. We know that we could also get it just as this ratio of polynomials that come directly from our difference equation. And we could also get it, right, by just solving this equation for h of z. So I could also get h of z as being the output, right? The zero state response outputs transform over the input transform x of z. So lots of different ways of getting this h of z. Probably for us, the one that's going to be the most simple, right, is that p of z over q of z. We usually have direct knowledge of that difference equation. So getting the transfer function h of z is a simple matter. And once we've got that transfer function h of z, we can do lots with it. We can find the zero state response. We can invert transform it to get the unit impulse response, all sorts of stuff. So let's look at a couple of cases here, just to maybe drive a few of these points home. Let's note the following. Note, if our input x of n is equal to a delta function, what kind of situation are we talking about here? We're looking at a discrete time system, right? So we have our discrete time system in here. We know that we drive it with inputs. It's just that in this case, we're letting that input be a delta function. That system, this is a linear time invariant discrete system. It delivers an output in response to that input. And if the input was delta, we know that output should become the unit impulse response. So if my input is a delta, what comes out had better be the unit impulse response. Well, how does this end up working in our transform domain expression that we just saw? We saw that what y0 state responses z transform was equal to, we had h of z times x of z. Let's look at this case again when x of n is equal to delta n. If I z transform that, this is a z transform we looked at before, z transform of a delta function, really, really simple, right? X of z in that case just becomes 1, right? And then that tells us that our output, the zero state response, is going to just be h of z times 1, which is h of z. And if I inverse z transform that guy, we find out that the zero state response of n, right, when the input is equal to a delta function, is indeed equal to that unit impulse response h of n, as we knew, as we expected. We know that this h of n and h of z, right, the transfer function and the unit impulse response are a z transform pair. Nice. Let's also remind ourselves that with that transfer function, because it has a explicit dependence on things like my characteristic polynomial q of z, right? We see there our characteristic polynomial forms the denominator of h of z, right? What do we know also about the characteristic polynomial? If you find the characteristic polynomials rich, you get the characteristic modes, and those characteristic modes tell us how the system wants to release energy. If those modes grow with time, the system is an unstable one, right? If those modes decay with time, it's a stable one. So we can also assess things like system stability just by taking a look at the denominator roots, what are called the poles of our transfer function. So h of z being equal to P of Z over Q of Z. We know that these polynomials have roots, so the roots of the numerator are the system what are called zeros. And if I look at the roots of the denominator are what are called the system poles. And we see that the poles, right, are just our characteristic roots. And we know we can use those characteristic roots to establish stabilities. So the poles tell us about the stability of our system. These are things that we've seen before, right? So for example, if the poles, right, are all inside the unit circle, we're talking causal systems here, right, things that we can build. If the poles are all inside the unit circle, we know that that corresponds to a stable system. If it's observable and controllable, we could say it's asymptotically stable. Otherwise, we would just say it's BIBO stable, right? We know if there's a pole outside the unit circle, right, that would mean unstable. And we know stuff about what happens if you have poles on the unit circle. That's marginally stable unless they are repeated, right, in which case it becomes unstable. All of those things that we had seen before could easily be assessed by this transfer function. Let's do one final example for this particular lecture. I would like to, again, just utilize my Z-domain knowledge in order to be able to take a look at a system that's first expressed in the time domain, and I would like to be able to find this particular system's unit impulse response. So let me set up the problem a little bit. So let's use, so this is an example. Let's use Z-transform methods, Z-transform methods to find unit impulse response functions. I'm going to do two examples. One I'm going to do is just a revisit of the example we'd seen before. We'd seen before this y of n plus 1 minus a 1/2 y of n being equal to x of n, right? I could look at this as an e minus a half y of n being equal to 1 x of n. The e minus a half is my q of e. The 1 is my p of e. And I have a standard form constant coefficient linear difference equation. I would like to find the unit impulse response. We had methods in chapter 3 to do this. I'd just like to do it with my knowledge now of transfer functions and being able to work with that. So in this particular case, writing out the transfer function h of z is absolutely simple. It's p of z by q of z. We've already derived that, right? P of z is just 1. Q of z is going to be z minus a half. So I have the system transfer function. It's got a single pole at a half. That single pole at a half is inside the unit circle, so this is also a stable system. I would like to be able to inverse transform this guy, right? Inverse transform that guy. And that inverse transform should deliver for me, with very little effort, the unit impulse response h of n. The only kind of quirk that we have in this particular case is that when I look at the function I had, 1 by z minus a half, it doesn't match anything in our tables. In our tables, we have things like a z by z minus a half. So if I wanted to get from 1 over z minus a half to z by z minus a half, I could do it just by multiplying by z minus 1, and then that would weight the z in the other. That's like a total component that would just be 1. Those are equivalent expressions. 1 over z minus a half is the same as z minus 1 times z over z minus a half. I know how this z by z minus a half inverts. That's in our table. That's just a half n to the u of n, half n u of n. And then z to the minus 1 just says delay that guy. So if I went ahead and did that now, I get what? I get a 1/2. There's going to be an n, but it was delayed, so an n minus 1 and a u of n minus 1, and I'm done, right? So much simpler to find the unit impulse response by utilizing transform domain techniques. You don't have to do any recursions. You don't have to remember any special initial conditions. You don't have to mess with all that kind of difficult, cumbersome methodologies that we saw in Chapter 3. It is just a very straightforward algebraic kind of solution. Okay, let's do another example. So we'll call this example 2. In this particular case, I'm going to go ahead and draw a system rather than give its difference equation. That'll change things a little bit. We'll have to do a little extra work, but this would be more reflective of maybe what you would see as far as if you were running through someone's code, you found out that a software designer had implemented a digital system. You might be able to back out the structure for that digital system, and then you'd have to figure out from that what it was doing. So in this particular case, I'm going to go ahead and take an input, and I'm going to let that input go into a summing node. We'll get the structure out, and then we'll make sure we get an understanding of it. The output of that summing node is going to deliver the system output. I'm going to grab that output and delay it. And I'm going to show a delay because now I know delays, at least transform domain, are represented by a z to the minus 1 term. So a very common way of describing a delay function is just to use a little block with a z to the minus 1. That just means delay by 1. So what comes out of that guy is going to be a y of n minus 1, right? And I'm going to go ahead and delay it again. So I'm going to run it through another delay block, another z to the minus 1 block, something like that. And what comes out of that is going to be y of n minus 2. And I'm going to utilize these in a feedback configuration. So this y of n minus 1, I'm going to run backwards, and I'm going to run it through a gain of minus 1, and it's going to get summed in to be part of this thing that I am adding into the input. So I've got this feedback path. And I'm going to do the same thing with my y of n minus 2. It's going to have its own unique gain, and it's a minus 1/4. I'm going to let it be in this particular case. We haven't talked yet about block structures for discrete time systems. We'll get to that more formally here shortly, but at least from a transform domain perspective. But we can certainly see how this system might work. So in this particular case, what do? I take an input, right, and I subtract from it the last output, and I subtract also from that 1/4 of 2 outputs ago, or the output 2 times ago, and that creates my new output y of n. So if I put all that together in equation form, right, I get something like this. My output y of n is equal to the input x of n minus the last output y of n minus 1 minus 1/4 of the output 2 units ago, y of n minus 2. So I did, through this structure, was able to derive out an equation that relates input and output. It's not in standard form, but I can easily do that. I'm going to just bring the output terms over to one side. So I'm going to have here a y of n, right? And I'm going to have a plus y of n minus 1. And I'm going to have a plus 1/4 y of n minus 2 being equal to x of n, something along those lines. That's a standard form constant coefficient linear difference equation in delay form. I would like to go ahead and write that out as something like this. It's a 1 plus e to the minus 1 plus 1/4 e, whoops, I'm getting ahead of myself. We're going to make this a 1/4 e to the minus 2 y of n being equal to 1 x of n. Now, let's go ahead and z transform that guy. The z transform of this thing, that polynomial up front is just going to have e's replaced with z's. So I'm going to get a 1 plus z to the minus 1 plus 1/4 z to the minus 2. Y of z is being equal to x of z. Why did I do this? Because I know that this transform domain expression can be handled algebraically, something I couldn't do with the time domain expression. We said that this example was all about trying to find the unit impulse response. It's a second order system. We know there should be 2 modes in there. We could certainly solve it with time domain processes. I want to do it with transform domain. So I want to get that transfer function, h of z. I know that because we derived this before, is just y of z by x of z, right? As long as we weren't dealing with initial conditions, which we weren't here in this case, which is p of z, in this case 1, over q of z, which is 1 plus z to the minus 2 plus 1/4 z to the minus 2. And I made a little mistake there. That first one has a z to the minus 1, something like that. So that's my h of z piece. If I go ahead and play with this a little more, I find out that that denominator, I want to find out what its roots are. We can see that is a z, not quite yet a z. This is a 1 plus 1/2 z to the minus 1 times a 1 plus 1/2 z to the minus 1. If I FOIL that out, I get 1, and then I'm going to get half z to the minus 1, another half z to the minus 1, that's just z to the minus 1, and then a half z to the minus 1 squared is going to give me a quarter z to the minus 2. So what we find out in this particular case is that the denominator has two roots, but they're the same roots, both at minus 1/2. So I've got a repeated root. We also know that our tables tend to deal with things not in terms of negative powers of z, but positive. So let's just multiply by z squared over z squared, get this guy so it's in a more standard form. So I'd have a z squared over, right, a z minus, and I'm just putting the minus here so I can get it closer to something in my tables. So in this particular case, I've written this out in terms of a z minus some root, right? So take a look at the denominator here, z minus the root, so z minus the root at minus 1/2. So I've got a repeated root at minus 1/2, and then I've got two zeros at the origin. That's the z squared piece up on top. I want to invert transform this guy. If you take a look in the tables of z transforms, either the formula sheet given on the class website or in the book itself, you'll find out that no table entry is exactly like this. The closest one that we can find, right? The closest one we can find has a form that does have that repeated root. So there is something about in the table a z minus some root. In our case, the root is minus 1/2 squared. But what it requires in the numerator is that root minus 1/2 times z. That's what's available in the table, and that's not what we have. We do have a z that we can lend to this. So if you look at our numerator here, there's a z squared, and I just need one z down here. So I could certainly give one of those z's to that and just leave the other z out front. Does that hurt anything? No, because a z out front is a z to the 1, and that just says advance by 1 whatever you had. I still need that minus 1/2. There was not that apparent in the original denominator, but if I pull out a factor of minus 2 times minus 1/2 does return to me that original numerator coefficient of 1. So I'm just playing some games here. I'm playing a little bit of mathematical games by looking in the tables to find out something that I can easily invert transform from the tables. This is very close to my original function in denominator, so I'm trying to get something that I can invert transform. And I needed to do some manipulation to make that numerator, right, match this desired one from the tables. That required a little bit of multiplication out front so that I could, in combination of these two pieces, still maintain what I had originally had, just a z squared. So I'm doing some algebraic manipulation so I can get something that is close to tables. What can I do with this? This piece here is a table entry, so its inverse transform is really easy. What does this piece out front say? It says minus 2 times an advance by 1 of that table entry, right? So that minus 2z to the 1 is something we can also easily handle. Now we're ready to invert transform this guy. If I take this whole thing and inverse z transform on that, the inverse z transform of the system or transfer function gives me the unit impulse response. That's h of n, right? That first one, the table entry on that one says that what we get there is an n minus 1/2 to the n u of n. We'll come back as to why that's sensible. And now we just need to multiply that by minus 2 and advance it by 1. So multiply by minus 2, so there's my minus 2, and then advance by 1. That means replace every n with an n plus 1. So there was an n out front, so it's going to become an n plus 1 out front. There is a minus 1/2 to the n. It's now going to be to the n plus 1. And there was a u of n, that's going to become a u of n plus 1. We advance everything by 1 because this z to the minus 1 acting on all of that, right, says advance everything by 1. That was the shift property that we had looked at last time. So this is my final result, and very simply gotten in this case, right? Got a nice, quick solution to this unit impulse response with very, very little effort. I do think I want to make one final note about this solution. While this answer is completely good, if you stare at it a little bit, you might become a little concerned about one term, and that's this u of n plus 1 term. If you recall, when we looked at this example to begin with, we drew a structure where an input xn went into some set of sums and scales and passed output values to create a new output. This is a completely realizable system. The only thing there are summing and scaling and delay blocks, all of which we can realize. This should be a causal system because it's physically realizable. It should be a causal system. And yet the impulse response that comes out of here seems to start at n equals -1, right? That seems to be non-causal behavior, and that would make me generally very concerned, having come from a structure that we know must be causal, that it is a realizable or implementable structure. Well, there's only one offending value here, that's at n equals -1. And if I take a look at what comes earlier, there's an n plus 1 term. If I put in n equals -1 into that term, I get -1 plus 1 is 0. So frankly, even though it seems for the u of n plus 1 to be something that starts at -1, that thing that it's starting at is actually 0. And so indeed it is not non-causal. It is not even really starting at n equals -1. It is completely equivalent to write this guy with a u of n rather than a u of n plus 1 because the n equals -1 is 0 in this case. Furthermore, if I take a look at this -1/2 and the plus 1 there, I can strip that guy out. That would give me -1/2 times -2. Those guys multiply together to just give me 1. And so I can do some further simplification in here. I can make this whole thing equal to then what? I'm going to have a not a 1/2 to the n plus 1 or a -1/2. I'm just going to have a -1/2 to the n. And then I would still have the n plus 1. That -1/2 to the 1 times -2 just canceled out. They became a 1. And this is a more compact, probably a little bit simpler version of what the unit impulse response is of this system. N plus 1 times -1/2 to the n u of n definitely emphasizes that it's causal, nice, clean, much more simplified expression, but completely equivalent to what we saw before. The last other comment I would make is that when we looked at our h of z, we noted that there was a root at -1/2 that was repeated. It was squared, right? And what happens when we repeat a root? A root at -1/2 should give us a term like -1/2 to the n. When we repeated roots, we saw this before, when we repeat roots, that's resonance, and a new mode should occur that becomes n times something like that. And again, we see that represented here as well. We had the mode -1/2 to the n. That's because of that root at -1/2. Because it was repeated, we get an n term on that, right? That resonance phenomenon. So all of this is showing up. It's all stuff that we've seen before. Next time, we'll talk about some finance problems. Should be pretty fun. We'll use Z transforms and our knowledge of Z transforms and the mathematics there to be able to make sound financial decisions.